Welcome back. The lectures for this week will focus on a very important concept called dissipativity. I would consider the lectures this week are as important as the lectures from the week of Lyapunov stability and Lassalle's invariant set of theorems, right? I mean, those deal with stability concepts and stability results and things like that, and this one is kind of for systems with inputs and things like that. We'll see in a second. And there have been many extensions and theories developed between, say, Lyapunov's 1892 work and dissipativity theory was somewhere in 70s, 1972 specifically. So in this gap of 80 years, basically there's been a lot of work, but this dissipativity theory papers in 1972 actually is a major step in terms of jump from applications to systems with inputs. So anyway, we will go through this concept of dissipative systems and then look at something called storage functions, and then we will also look at something called extended KYP conditions, which will look very different from what we have seen in the case of positive real, and then we will look at some special cases. This is for this lecture, right? So we'll take a motivating example, so to speak. So we will consider this mechanical system, which is modeled as spring, mass, and damper. And the model for such a spring, mass, damper system is very well known, and it happens to be mx double dot. That's the inertial side, and then you have a damping cx dot, and then plus a elastic component of the spring component coming a time, and this is typically perturbed by an external force. U is the notation that we use for that force, right? So in all the theory that we have developed in last several weeks, basically we ignored this external force at all. So in this particular lecture, and then perhaps all the other lectures, external input is going to be considered. In some cases, this external input is something within our control, so that becomes control input, so we can actually pick and choose what it should be. On the other hand, it could be a disturbance in something that we don't have any control over, and then we have to just hope that the system is going to be stable in spite of some input coming, and obviously different types of inputs will produce different kind of behavior and things like that. So dissipativity is a theory that talks about how systems behave in the presence of inputs, and in this example, let's call y of t as output. We use the word u as input. It's somehow influencing the system. Y is simply a measurement that we take. In this particular case, the measurement that I take is only for the first derivative of x, and then in physics basically we call that velocity, and call that as output, right? And then we denote that by y of t, and pick your quote-unquote Lyapunov function, which is energy function, right? But I'm going to go beyond Lyapunov stability because we have input and things like that. I mean, it's a simple exercise for you to check if when u is not there, this system is going to be Lyapunov stable to start with, and then basically we can further move and then move forward, and then basically show using Lassalle's invariant theorem that this is an asymptotically stable system. I mean, we have seen probably some special case of this example at some point, right? What's interesting is this kind of analysis even extends if these were matrix models where M, C, and K are typically symmetric matrices, symmetric non-negative or positive definite matrices, and x happens to be a vector, and u will be their force vector in that particular case, and your energy function will become half x dot transpose m x dot plus half x transpose kx and things like that, right? So for simplicity we pick a scalar, but this analysis works very well even in the multivariable case, and then let's call that as an energy function, but in reality it's probably a Lyapunov function and things like that, right? But here we are interested in the case where we have input, so we take the time derivative, the v dot, the usual one, so that's simply taking the derivative of this particular function. We get mx double dot x dot plus kx double dot x dot, right? And in both these things x dot is common, then when you actually take that common thing, basically you'll get mx double dot plus kx, and from that equation we know that that's nothing but minus cx dot plus u, right? So you get the first expression from that part, minus Cx dot times x dot. And then the second part is u of t times x dot. But as you know, basically x dot is nothing but y. So I chose to write that as u times y, right? And so we can integrate this expression, right? V dot is equal to minus Cx dot square plus u times y. When you integrate it, we will get the final value of v is equal to the initial value minus this integral value of Cx square dot plus this integral from 0 to t of this u times y. Okay, so let's look at the physical understanding of this, right? So this uy, right, force times velocity. Those of you who remember physics, basically force times velocity is nothing but power, right? And integral of power over time is basically power is nothing but rate of energy. So integral of 0 to t is energy. But this is the external energy input, so to speak, right? So whereas V of x is kind of the internal energy, it's the summation of kinetic and potential energy. It had some internal energy at the start, and then basically the final value is V of x of t x dot, right? It's going to be the final internal energy. So what this equation is saying is basically the final internal energy is going to be equal to let's say for the moment C part is 0, right? Then basically the final energy is going to be equal to the initial energy plus whatever the external energy that is put, right? It's possible that this C is non-zero, and then typically when we say damping, we understand that is some energy is lost through that process of damping. Another nice word that we can use actually for this energy getting lost is the word dissipation, right? So that's how the word dissipative systems comes and things like that. So this equation is quite important for us to understand. Is basically the final energy is going to be always less than or equal to initial energy plus the external energy input, or through power, basically supply. You have some energy supply from outside. And in the case where C happens to be 0, that there is no damping or dissipation, then this becomes an equality, and such systems we call them as lossless systems, right? I mean, there's no loss at all in terms of energy, right? So we take this as Q. So basically, when we have inputs, unlike say when we don't have inputs, the inspiration for Lyapunov stability was, okay, find this Lyapunov function which is acting like an energy function. So if that is bounded, then basically the system is going to be bounded, and if that's going to decrease throughout time, basically we will end up with a asymptotically stable system, especially if that V happens to be going to 0, right? So if energy is at some level to start with, and then if that energy gets dissipated without any external input, it will reach an equilibrium point, and that's what the basics of Lyapunov stability. Whereas when it comes to something with input, the scenario is slightly more general, and basically the final energy is going to be less than or equal to initial plus whatever the energy supplied from an external source, right? So this is an understanding from physics, and then there's nothing so deep about it, at least after thermodynamics has been discovered, so to speak. I mean, once first law and second law were discovered, a lot of concepts of energies have been cleared in this the Lyapunov stability and things like that comes about 30-40 years after that. So people already knew about a lot about this energy and things like that, including external inputs and things like that by the time Lyapunov stability theory came. But people were focusing a lot on basically systems with no input, because if we can at least understand the behavior of such systems, then the step of introducing input is hopefully not so bad, right? So, and anyway, I mean, throughout these 80 years that I've been talking about between Lyapunov stability and dissipativity theory, people have discovered basically things like disturbance rejection. What if this U happens to be some disturbance? Can we guarantee something about boundedness of this particular system compared to that, and things like that? We will address some of those questions from a mathematical perspective in the next the several minutes, or even next lecture and things like that. But the understanding of these concepts from physics has been there. Now, in 1972, Professor Jan Willems took the major step of actually consolidating all such concepts and then extend it to an abstract notion of dissipativity, which we will introduce in a second, right? So how do we define a dissipative system? So I take an approach, a simpler approach to start with, and then abstract approach at a later point, right? So here we jump now with systems with input, and then x dot equals f of x comma u, and there's some output y equals h of x comma u, okay? And these functions at this point are not as important in terms of definition. So I'm going to define, and then it's full of terminologies, one of those very picky things, but the definition itself is quite intuitive. So we call a system, this particular system G, as dissipative with respect to supply rate, and has a storage function V, okay, if this inequality is satisfied. So I should have mentioned storage function Vs, but I don't mention that, but I think it's obvious from the inequality there. So if the dissipation inequality, which is this inequality, is satisfied, okay, what is the dissipation inequality? It is kind of imitating what we just saw. The final storage function, which is another name for energy function. I mean, that's the way Professor Jan Willems chose to call his energy function, is going to be less than or equal to initial storage plus the energy coming in from the external source, which he calls by the name supply rate, right? This R is supply, it's a rate of energy that is supplied to the system and then basically integrated over time, right? So it's simple enough. I mean, it's just basically a system that satisfies some kind of energy dissipation inequality. From a conceptual perspective, it is quite straightforward, intuitive, but of course, we hope that this means something for us, and then we will have many implications of this kind of assumption and things like that. So in that sense, this is not a very general system. We're not leaving this system. We are defining a special class of systems through this particular function called supply rate, and for which there is something called a storage function and satisfies this inequality. So it's not a wildly behaving system, but actually very well behaved for a given supply rate, right? One of the questions that immediately pop in mind is, given an arbitrary system, can we actually identify some supply rate where this kind of rule is satisfied? And we will not address that question and leave it as a food for thought for you, right? So anyway, we call this y as output and then u as input, and then this inequality, of course, is satisfied on solutions that are coming with the initial condition x sub 0, and then y of t is function of x and u, right? So that x is coming from the solution of the differential equation x dot equals f. So that's how each and every element is connected to one another, right? So if this inequality, instead of inequality, if it is exactly equal to one another, then we call that system as lossless, right? With the same supply rate and the storage function Vs. Okay. Now there is an additional concept, and this is you can blame it on my dissertation. Basically, we define something called exponentially dissipative, and this becomes very useful in designing controllers and things like that. Or some plants, some systems have this feature naturally, and it's simply an extension of what we see in the dissipation inequality with an exponential weight, and it has certain implications which we will discuss a little bit later, but it turns out, if you're curious, basically these are, if you recall, positive real versus strict positive real, that this is the strict positive real version of the dissipativity. Okay, so what else can we say? Now we have this definition of dissipativity with respect to the storage function, and that storage function, let's say if it happens to be differentiable and things like that, then we can actually take the same inequality but take the derivative with respect to time and then put it much simpler form, which essentially says the rate of change of internal energy is always going to be bounded by the supply rate R of u comma y, right? Once again, given a system, can we always find a supply rate such that this inequality is satisfied? I will leave that as a long-term assignment for you to think, to come up with examples and things like that. But here we are saying a system is dissipative with respect to the supply rate if it has a storage function such that this dissipation inequality is satisfied. This and of course the integral version that are one and identical in the case of differentiable storage function, right? So this may be interpreted as external power input is always going to be greater than or equal to the rate of change of the internal, and then the gap is what we call as dissipation. If there is a gap between say what is supplied from outside and what is getting accumulated inside, that is what we typically call in physics as dissipation, something that just getting lost where we don't know. And from thermodynamics we know that most of it is getting lost through heat and things like that, but here in mathematical definition we are not interested, so we simply call that as dissipation. And if that dissipation is not there, in other words basically V dot is equal to exactly R, then we call such a system as lossless because there is no dissipation, right? And then the exponential dissipativity definition simplifies to this expression, no exponential weights anymore, but you have this nice V dot less than or equal to minus epsilon V, and then this is kind of a hint why we chose to introduce that particular definition. This allows us to prove many of the asymptotic stability results from the first part of the series, right? So in that sense it's not motivated from physics but more from the requirement that we want these nice properties of asymptotic stability and things like that. Slowly we will see that basically when the plant itself doesn't have this asymptotic stability behavior in the absence of inputs, we will choose to have actually a controller that satisfies that, and then we ensure that the overall system is globally asymptotically stable and things like that, right? So that's the basic definition of a dissipative system. So what we will now look at is special cases, right? And these are very important special cases, and we now introduce the definition of dissipative and specialized, but historically these were already kind of known notions, and then Jan Willems when he introduced the concept of dissipativity kind of generalized to an extent where these things certainly are special cases, right? We call something as a passive system if it is dissipative with respect to the supply rate 2U transpose Y. If you basically remember the example, the spring mass damper system example, we essentially have V dot less than or equal to U transpose Y. 2 or not, it doesn't matter. If you put 2, then we scale up the energy function twice and things like that. It is a matter of choice whether you want to call it passive with 2 times U transpose Y or U transpose Y. In fact, it's obvious that basically if something is passive with respect to the definition of 2 U transpose Y, it will be passive with respect to U transpose Y alone, right? And this is an example, but people realized importance in multiple scenarios, originally coming from electric circuits where U and Y are such that the product is power. So for example, one of the variables could be current and the other one is voltage, and then the product becomes power, right? And so basically these concepts were I believe developed from the power systems perspective, and then they called this passive if you don't have any active elements and things like that. If you have active elements, then things get a little bit more complicated, and then all these passive systems have some kind of dissipation, and so that's how they realize the gap between, say, accumulated power versus internal supply and things like that. So these were already well-known concepts, and then in fact the positive real lemma and all those things were developed in that particular context, right? So a lot of this framework was existing. Now and there are mathematical notions introduced for sake of understanding some strict nature of these particular systems. Like I said, any of these strict notions are kind of forced definitions from the perspective of stability and things like that. So we call some system as input strict passive if the supply rate is modified by this minus epsilon U transpose U, where epsilon is some positive number, right? So anyway, for each of one of these things, we can imagine the exponentially weighted versions also. If we understand the basic version, the exponential version is relatively straightforward. So we call some system as output strict passive if the same thing is true with minus epsilon y transpose y, and you can imagine you can combine the two and then call something as input output strict passive if both these terms are there, right? And finally, slightly unrelated, something called non-expansive, right? It's a very different concept from passivity. We will look at the implications of this in a couple of minutes, but we call something non-expansive if it is dissipative with respect to the supply rate, which has this interesting form gamma square u transpose u minus y transpose y, right, where gamma is some non-zero number. Suppose if gamma is 1, then that's simply u transpose u minus y transpose y, which is non-expansive definition originally, right? So let's actually start thinking about, can we say something about stability of any of these systems in the absence of inputs, okay? So for which basically I'm going to assume that the storage function that we have in the definition is actually positive definite. That means v of s of 0 is 0, and then v of x is positive for all non-zero x, right? So then one of the interesting things that we can immediately conclude, so recall that v dot is less than or equal to r of u comma y. In the case u is 0, that simply becomes r of 0 comma y, whatever is coming out of u for that u. But more generally, for any arbitrary y, if the function r is such that r of 0 comma y is less than or equal to 0, then what we can show is g is dissipative with respect to that particular supply rate. Then the zero solution with u equals 0, undisturbed system, is going to be Lyapunov stable. And if have exponential dissipativity, that implies asymptotic stability, right? In some cases, we actually get asymptotic stability without even exponential weighting. We'll discuss that in maybe a minute. So therefore, what can we say about any of the special cases that we discussed? Well, let's go back and look at these things. So if u is 0, r of u comma y is 0 in the case of passivity, right? In the case of input strict passivity, same thing is true. In the case of output strict passivity, we get this part as 0, but then the r of u comma y is minus epsilon y transpose y, which is of course is less than or equal to 0 for all positive epsilon. Same thing is true about input output strict passivity. What about non-expansivity? Same thing. So all these cases happens to be cases where these are generalization of stable systems to start with. Like I said, some of them could be shown as what you call the asymptotically stable case, right? So anyway, I kind of separate it out between the passivity and other non-expansivity. But one of the first remarks that we have to understand is, if a system is input strict passive or output strict passive or input output strict passive, they're all passive, meaning they're more than passivity. So that's a trivial observation, but it's important observation. And if something is passive, then the zero solution is Lyapunov stable, right? Like I said, in some cases, we can actually show asymptotic stability. How do we know? So r of u comma y is, say, when u is equal to 0, so for example, output strict passivity will give you minus epsilon y transpose y. So we get the inequality v dot is less than or equal to minus epsilon y transpose y. So through Lassalle's invariant theorem, we can show that y will become 0. So the invariant set theorem will belong to the set where y is 0. And suppose y is such a way that if y happens to be 0, somehow we can connect that to x being 0, then we can guarantee asymptotic stability. And then some of those concepts they're quite useful in proving asymptotic stability in many such cases. Anyway, so like I said, passivity, non-expansivity, input strict, output strict, input output strict, all of them will satisfy this asymptotic stability. If the definition is true in the case with the weight, then basically the conclusion could be, in the absence of any input, these systems will be asymptotically stable also, right? So the notion of kind of these passive systems and non-expansive systems were motivated from, especially the passivity and things like that, were motivated from physical systems. And then it's nice thing to note that all of them were stable to start with, and then when you put a input dissipativity, we get this particular definition. And it's kind of nice behavior, and we're taking nice systems, and then basically if some system, an arbitrary system, satisfies any of these properties, they will remain stable, right? But the non-expansivity, the history is basically came through different ways of looking at these things. Basically, can be viewed as actually a input-output stability result. So because we can show, in the integral form, basically the final energy is less than equal to that gamma square u transpose u minus y transpose y. So when you actually realize that if v is non-negative positive definite, then basically we can simply conclude that the integral of norm of output square is always going to be gamma square times integral of this norm of ut square. And then I want you to look at the inequality of the dissipation and then come to this particular inequality, right? Show that yourself, and then which essentially implies that if you have a system that is non-expansive, then the system is going to be bounded input, bounded output stable, right? Now this is a very crucial definition in one sense. The original definitions of stability in the classical control case started with this bounded input, bounded output stability, right? Though Lyapunov stability was already discovered, it was kind of still not very well known. And people use the notion of bounded input, bounded output stability for linear systems, and then eventually expanded the definition to nonlinearity. And Willems kind of subsumes that notion through this concept of dissipativity, special case to non-expansivity, right? So in that sense, these special cases of passivity and non-expansivity are quite important. On one hand, the passivity is like a very natural notion for any of the physical systems, especially that satisfy the mechanical and electrical models. And then of course non-expansivity is kind of a nice generalization of the bounded input, bounded output stable. But the general notion of dissipativity is far beyond any of these notions, but these are still very important special cases, right? So now I want to make a very important remark. So we have seen basically dissipativity is kind of a generalization of many of these interesting concepts of positive real or passivity, or bounded real and non-expansivity, bounded input, bounded output stable, and things like that. What about static systems? Suppose if it is not a system that is described by differential equation. So we'll consider the linear static systems, basically where you'll have a typical matrix delta, and for that particular system, it's a static system. The input is u and output is y. So there is nothing like a state and equilibrium and things like that in this particular case. So we can kind of think of this delta being dissipative if it satisfies this dissipative inequality, right? So if this r of u comma y, right, where take that y and then put delta u, if that satisfies greater than or equal to 0, then we say that delta is dissipative with respect to supply rate r of u comma y, okay? But in this particular case, you'll have the inequality r of u comma delta u greater than or equal to 0. It's a fairly straightforward inequality to check, right, typically. So in the robust stability analysis, if you recall, we had expressions that involve, delta transpose q something, right? So that's essentially, kind of using this concept of dissipativity for that special case. Though we introduced that ahead of dissipativity concepts, you can go back and actually look at those lectures and see some of the inequalities. Delta transpose delta is less than or equal to gamma square identity and things like that. All of them boil down to understanding through this static systems. We also looked at actually one more important static system, which is coming from nonlinearities, where y is this phi of u, and again we call this phi as dissipative with respect to supply rate if r of u comma phi of u greater than or equal to 0. So again, all the sector nonlinearity stuff that we looked at in the absolute stability problem belong to this category. So this slide is essentially saying one important statement. All the concepts that we showed in robust stability as well as absolute stability problem are a special case of dissipativity theory. So if you understand dissipativity theory, they become quite trivial, but of course ease of understanding those things is there because it, a lot simpler than dissipativity theory. So that's why we kind of focus more on those special cases, and we have many methods to check and things like that. Most of them are LMIs and stuff like that, so we can actually go back to the computer and solve it. But there's no reason. I mean, these are just basically the parts that come into a nonlinear system as feedback interconnection. So therefore, in the next part of this week's lectures, basically we will look at feedback systems, feedback of two dissipative systems, and one of them could be static. So which is essentially what we did in the robust stability case. So we looked at as a feedback of a system G of S, and in the feedback we have this delta, which is a static dissipative system. So the conclusion eventually we'll make is basically if G of S happens to be dissipative and then D happens to be delta happens to be dissipative with respect to certain supply rates, we can show that the overall closed loop system is going to be stable. And absolute stability theory is exactly identical in the sense that we take a nonlinear system problem, divide that into a linear plus nonlinear, where the nonlinearity actually satisfies some kind of sector condition, which is essentially saying that the nonlinearity part is dissipative. So what would be a sufficient condition for that particular system to be stable? The linear part has to be dissipative, right? So that's how the positive real lemma and all those things got connected to absolute stability problem.